Well, welcome everyone to our latest webinar in our webinar series for 2024. It's an absolutely great pleasure to host these webinars. Sharing of knowledge is such a part of what we do at Stormwater 360, and the world of stormwater, and especially stormwater quality, is so wide and vast that there's always new things to learn. And it's a great pleasure as well to have Mike Hanna, our technical director and founder of Stormwater 360, join us to present on some of the work that he's been doing and the knowledge that we've got over the past 25, 26, 27 years of working in stormwater treatment. I guess it's good to ask the question, why are we talking about this? Why are we talking about evaluating treatment devices and treatment device performance? We've already spoken about similar topics in similar webinars. We already have similar conversations with a lot of the people that will be watching this webinar. So what is the relevance? Well, it's a common question that we get asked very, very regularly is, I have to achieve this outcome. What type of device can I put in to remove this type of contaminant? What type of device is going to achieve this percentage removal? And what one device is tested to do in one point and one location isn't going to apply, say, from Auckland to Christchurch. There are differences across the regions and differences where the tests are done as well overseas. And so what Mike is going to do is talk through a little bit of the things to look out for, how some of those test protocols are undertaken and what they specifically test for and how they test. And we're going to talk through how that's applied to New Zealand and what to look for New Zealand applications. So a little bit of housekeeping if you haven't been to our webinars before. If you have any questions throughout, as we go, please put them in the chat. I'll be able to see them, and there'll be hopefully good time at the end for question and answer session. So yeah, just type those into the chat. And without further ado, it's a great pleasure to introduce Mike. Mike has, as I said, he's been leading stormwater treatment in New Zealand with Stormwater 360 for almost since the inception of stormwater treatment in New Zealand. And he's no longer only working in New Zealand. As a company, we have a group of companies that work in Australasia, the Pacific, and in the Americas. And Mike has been up at 4 a.m. for I don't know how many weeks now, working with the Testing Society in America to introduce a new standard for the evaluation testing of catch basin treatment technologies or water quality inlets. And Mike is in fact leading the writing of the American standard for testing of water quality inlets. So we do know a thing or two about how to test and how to apply that to treatment technologies. Slightly more locally, Stormwater Australia have asked Mike to attend their conference to talk about the work that he's doing in America with STEP and applying that to a review of the Australian evaluation process, SQUIDEP, which there is being looked at in various places. So Mike will talk about all of that in much greater detail, and it's great to hand over to you.
Thanks, mate. Can you hear me?
Yep.
Good, great, awesome. Now I'll just share my. Are we going to do a poll, or we flag that?
We are going to do a poll. Fantastic question. So I think the first poll is: have you had to evaluate the performance of a stormwater treatment device before, either for a project that you've done, or maybe you work at council and you've had to look at device approvals? Nicola, if you could bring up that poll. So have you had to evaluate the performance of a stormwater treatment device before? Have a think about that and we'll bring the poll up.
Uncomfortable silence.
Maybe if there's technical difficulties, maybe just give us a show of hands. Raise your hand if you've had to evaluate the performance of a stormwater treatment device.
Oh, there we go.
There we go. Lots of people raising hands.
Well, yes. Well, Well, that's good to see. There's a lot of evaluation going on. Well, there's the poll, but I think we can skip that now and get into it. Yeah, so this will be really appropriate for you guys, and we're probably as more and more innovation comes to the industry, I'm sure more and more of you will be asked to evaluate new and innovative stormwater BMPs. Now I will jump to my presentation. And I'll go to that, I'll get the pointer going. Yeah, so evaluating a stormwater treatment BMP performance. Just a quick overview. Evidence of BMP performance is often required by city or regional councils in New Zealand, and also by other agencies such as Green Star in order to get accreditation. This presentation will review the different methods for evaluating a stormwater BMP and the performance data that may be given to you. It highlights the complexity of issues in evaluating stormwater BMPs. And I'm going to focus on total suspended solids first. It's probably the most regulated suspended solids and arguably the easiest. We're going to discuss different sort of evaluation protocols because there's protocols been developed to address the complexity of the study of stormwater. And the whole point of this is to give encourage a higher degree of professional judgment in the choice and the application of different stormwater BMPs, making sure you're getting the right BMP for the stormwater problems you have. Okay, how do I go next? Here we go. Just run through the agenda. It'll be a bit of an intro. I'm going to talk about the 3 key factors to BMP performance. And I'm going to talk about total suspended solids, talk about complexities with other contaminants such as nutrients and metals, and even emerging contaminants such as PFAS. We're going to look at performance testing, this evaluation, verification and certification programs that are around to give confidence in the data that you may be given. And we'll touch on the different programs. And we also look at how we would apply performance data from studies elsewhere to a local catchment or a local project that you might have. And then we're going to talk more about other matters apart from like performance, removal efficiencies, etc. And then I'll conclude with some advice and maybe some guidance on tools. So stormwater is a problem. We all know that. There's a larger variability of pollutants in stormwater. Anything that lands on a road or a hard surface will be washed off and inherently will probably become a pollutant. Different catchments have different pollutants of concern. You know, there's some catchments are more sensitive to different stresses, and different land uses produce different pollutants. And all the pollutants actually have different physical and chemical properties, which affects the way they impact the environment, but it also affects how we can remove them out of the stormwater. So it's quite challenging and complex. And there's new technologies now being developed with lots of different treatment mechanisms to target this wide range of pollutants and their variable character. So the big challenge is how do we evaluate these new technologies? Because really we need them. Our current suite of technologies and population growth that we're experiencing, we can't really stop the degradation of stormwater as our population grows. So 3 key factors to BMP performance, that's concentration, load, and volume reduction. So pollutant concentration is a variable that really influences efficiency or percentage removal. Environmental regulations usually are based on load reduction, because usually they're developed for example, 75% on an average annual load, or they're developed from looking at a receiving environment and how much load it can handle and be resilient to. Load is a function of concentration times the volume of runoff. So the reduction of runoff is another method as well as for reducing load. Not only reducing the concentration, but reducing the amount of runoff is another way of reducing the load. So this figure is a good example of how percentage reduction, how the performance of a BMP could really be misunderstood. Here in the slide, 50% removal is better than 80% removal. And that's because the 50% removal scenario is actually discharging less pollutant load into the environment. The figure highlights the risk of percentage reduction, looking at percentage reduction as the only metric in evaluating performance of treatment devices. Unfortunately, many of our regulations only list 75% removal, but give no further explanation. So it's really hard to really quantify what we're trying to achieve. This figure also suggests that concentration influences performance, which is true, and I'll demonstrate that some more. So here's some performance data for the storm filter. The storm filter is a filter that Stormwater 360 provides. I think there's about 4,000 of them installed across New Zealand now. And during the process of getting approved by Auckland councils and other city councils across New Zealand, a lot of performance data was done nearly 20 years ago in Washington. And each dot here is a storm that they sampled, different projects, different studies here. And there's influent concentration across the bottom and percentage removal on the y-axis. On the y-axis. Now, the results kind of show that when you get up to around, let me just turn my laser pointer on. When you get up to around 300 milligrams per litre, we're getting 90% removal. And that's awesome. But unfortunately, stormwater is not, the typical stormwater concentration in Washington is more like 100 to 200 milligrams per litre. And so that's why Washington has approved us as only at 80% removal. So it's really highlighting that, you can't just say percentage removal without thinking about what your normal influent concentration is. Or if someone gives you some data showing that they've got 90% removal, you need to look at what that concentration was to give that performance. This is for suspended solids too. Now, I'm sure everyone on the webinar has heard of the first flush phenomena. This is where, contaminants, majority of contaminants are washed off a hard impermeable surface at the start of a storm event. This phenomena highlights that concentration can actually vary in a storm. And a BMP might get really high removal at the start of a storm, but not so high a removal at the end of the storm. And so it highlights the importance to monitor a whole storm event. You can't really just look at the start, because that would be a little bit misleading. And you need to, especially if you're looking to quantify the load being transported, you need to look at the whole storm event. Here's another slide showing first flush, where numerous samples have been taken from the influence across the top, and effluent is below this device, is across the bottom. And it shows that that if we were just to be taking, this is all the samples that we take in a full storm event, if we were only just to take one sample, it would really depend where on the storm it would be to what percentage removal we got. So if we just took one sample, and it happened to be number 3 here, we'd get 80%. But if we took, at the time when number 9 sample was, we took number 9, we'd get 0% removal. So it kind of really, again, shows that they really need to take lots of samples right through the storm, because the concentration will be varying, and you want to capture all that variability when you monitor stormwater. But I'm not over talking about concentration. We also find it varies with rainfall. Here's another first flush, another storm. There's first flush here at the start of the storm. Down here is a graph of flow and when the samples are being collected. But this storm, it picked up in intensity later in the event as well. Rainfall is variable. Who knows what's going to happen? And it got more intense later in the storm, and we saw a second pulse come through. And what we find, the harder it rains, the more load or more higher concentration you'll have, unless it's already been washed clean. There's a lot of variables at play. But what this is showing is that you really need to make sure that your sampling is in step with the flow. So if it rains harder, you may get higher loads, so you need to sample more. So this really shows the need for flow proportional sampling to capture that concentration variability. Now we've considered concentration. Now let's look at how we're going to reduce the load or the volume, as I mentioned in the start. Volume reduction is another way of reducing load. So volume reduction is achieved by retention, and that's infiltration, evapotranspiration, or water reuse, or stormwater use reuse. Green infrastructure solutions have the ability to reduce runoff more. They can be designed to infiltrate. The plants in them allow evapotranspiration into the air. So this is an added advantage of green infrastructure solutions over simply concentration reduction. The figure on the screen shows two scenarios. One with a flow through, say, a filter, a stormwater filter, and the other one with a bioretention system in the same catchment. The flow through filter, say it gets 50% removal, so we will have 50 kg being discharged into the environment. The bioretention system has 50% removal as well, but also has retention of 50%. It has, say, 25% evapotranspiration and 25% infiltrates into the ground. So the total amount of pollutant being discharged into the environment is only 25 kg. So that's really a 75% removal. So it's important to consider if there's what this highlights too is that you really need to measure the flow upstream and downstream of the device and look to see if there's any volume reduction happening as well. So now let's get on to the challenges. So that's what we're trying to do. We're trying to really ascertain load in and out of a certain pollutant. And so now we're really looking at suspended solids. So suspended solids, as I said, is arguably the easiest to measure and probably the most regulated, so it's a really good place to start. So I thought, well, why do we actually regulate suspended solids? So it's really important to realise that urban stormwater suspended solids are not like the suspended solids that are maybe referenced in ANZAC guidelines or other environmental assessment reports. Stormwater sediments are toxic. They are a surrogate from other contaminants like heavy metals or nutrients and etc. They often attach and stick to the sediment. So why suspended solids toxic sediments are a real issue in stormwater is that when they get to the receiving water body, they settle onto the seabed or the estuarine bed or the riverbed on the floor. And then on the sediment settling on the ground has these attached contaminants in it. And in between, as it settles, in between the particles on the seabed, there's little gaps where what we call pore water. And now if the piece of sediment has a bit of say, heavy metal attached to it, there might be a little bit of organic in that water as well. That'll become anaerobic inside that pore water, and that releases the heavy metal into a dissolved form and more bioavailable form in that pore water. Now, what else lives in the seabed and the bottom, all the bottom of the food chain essentially, and that allows the heavy metals to be transported from the land into the food chain of the marine environment or the freshwater environment and travel up the skin. So that's why TSS was really the first one that they really jumped onto, especially in Auckland, and I'll talk a bit about that in a minute, because we have estuarine environments and that, because it is a surrogate for other contaminants, but it's also the impact of it when it was settling and landing in the receiving environment was the big problem. It's really the main transportation mechanism for contaminants, sedimenters. So where did that 75% in Auckland come from? And I thought we might take a little jump back down memory lane. Back in the 1980s, it was identified that the largest impact to Auckland's environment was the stormwater sediments on our estuarine environment. Because Auckland has huge estuaries everywhere, 2 harbours and a lot of estuaries. And so it was so the regional council decided that, well, okay, we've got to bring in stormwater regulations. We've got to stop this amount of sediment being in our estuaries. So at that time, there was only really one way of treating stormwater. Well, the current knowledge was doing big detention ponds. And TP04, technical publication 4 by the Auckland Regional Council, went out and did a whole bunch of particle size and sampling of stormwater, and to determine the particle size of sediments in Auckland, and did some testing and calculated the fall velocities of those sediments, and basically then sized what size stormwater treatment pond would we need to remove sediments in Auckland. And so they did that, and then they, okay, well, how we could get 100% removal, if 99% removal if we sized it really big, or we could get it 50% removal if we sized it really small. And so they did a modelling exercise, and they looked at all the different sizes, and then they found there was a real inflection point at about 75% removal of sediment. After that, the cost of increasing the basin size was really not economically feasible. The return you got for increasing the basin, you'd almost need to double it to go from 75 to 85. So it really wasn't working. So that's how they set the 75% TSS removal. It was a rule really for Auckland. It was specific to the needs of Auckland and the issues Auckland had, i.e. contaminated sediment in the estuary. And so that was how it was created. And it kind of just highlights that these rules are based locally and specifically for the contaminant we're dealing with. I don't really know what time I am, but if someone could keep it, Matt, if you could let me know I'm going on time. So let's talk about some of the other challenges with TSS. And the first one is definition of TSS. Regulators don't usually define TSS. They say you must get 75% total suspended solids removal, but doesn't really explain it. And you also see many suppliers or may give performance data, but they fail to define what they actually mean by suspended solids or total suspended solids removal. Solids are actually transported in many different forms. They can be really large gross pollutants, over 5 millimetres. They can be grit, between 1 and 5 millimetres. They can be fine solids. They can be organics that are really light, and there's even soluble solids. Some definitions for suspended solids say under 262 microns, some say under 500 microns, some say all particles in stormwater. I've even seen some reports where people say, oh, everything on the road is potentially a suspended solid one day. And so they sweep the road and they test their device with that. And I'm like, well, that's not really cricket. But yeah. So really, so the methods for how do you measure suspended solids? Well, the original term total suspended solids, it's actually a method adopted from wastewater. Total suspended solids is a method. The method adopted from uses a pipette to subsample the sample. And that's because when wastewater, the density and the mix of the solids in wastewater is pretty consistent and pretty homogeneous. In stormwater, it's really a lot more variable and different. So when you use the wastewater technique on stormwater, you find a lot of the heavier stuff like asphalt wear or drops to the bottom, and it was undersampled in that method. So they've developed a method called suspended solids concentration that is used to measure suspended sediment in the US now in most of the testing protocols. There's some variations. For instance, some regulators require you to have only under 500 micron suspended sediment concentration. I forgot to explain that. But suspended sediment concentration, instead of using a pipette for just a little subsample, you use the whole sample, the whole 1 litre bottle or the whole 200 ml bottle you use. You tip it all in so you get the heavier stuff that falls out at the bottom as well. And here's a picture of a whole sample being filtered. It takes longer, but it's more, this is the sediment that has been transported in the storm. But it's important to make sure you quantify those whole samples, because it's important that we really look at the finer particles as well as the coarser. When I say coarser, I'm still talking under 1 millimeter, because finer particles typically have a higher concentration of other contaminants such as heavy metals or phosphorus. Finer particles also take longer to settle if it's a settling device. And also particle size varies with location and also land use, but it also and say the Portals in Christchurch, it's a very fine soil, so the sediment off in the stormwater over there is finer than say the sediment in Auckland. So it varies by location. So performance can be overestimated if you only look at coarse particles. So if someone gave you stormwater data and they don't give you the particle size distribution, we'll say, oh, we got 90% of sediment. That might be really stuff over 500 microns, which is really not really that toxic. It's pretty inert. So usually when we look at testing devices, we want to have an average of around 75 micron for a 50% mark of TSS. So there's also an influence of how the operating rate of a treatment device. So if you're looking at performance data and someone gives you suspended solids data, and this shows that if a device is excuse me. If a device, okay, let me start again. So this slide shows how the different particle sizes are removed by different operating rates of a treatment device. This is some lab data from Vortex GPT, and this say the device works at 10 litres a second. This is working at say 2 litres a second, 4 litres a second, 8 litres a second. Depending on the size of the particles that we're looking at and the operating rate, there will be a different removal rate. So if we think of 75% as normal, here this device really has a treatable flow rate of, if we're trying to get 50%, probably 6 litres a second. So if I got data from someone showing from a report and it was only operating at 2 litres a second, and they gave me 250 micron data, it would look like I was removing 99%, and I would think, geez, that's great. But if I look closer, if 75% is normal, this product device is actually only really removing about 50%. And that's actually happened to us before. We had a vortex that we tested in the field with coarse sediment, and it got 90% removal, but it only actually got approved at 60% removal because it was much coarser than what was normal for the location. It's also important to look at the removal efficiency of TSS for a storm in the context of, that's just what I said, the design flow and what it's meant to be operating at. So you can do this in the lab, but you can also do it in the field, which I'll talk more about later. Another challenge that's often overlooked is also fugitive solids. Fugitive solids are large solids that may come into a device and not get monitored at the start. Organic material is a good example. A leaf might not get picked up on an automatic sampler, but it ends up into the system. But then it breaks down and turns into mush and then transforms and is released either as a finer particle or as orthophosphorus. So it really highlights the need to make sure there's a sufficient dry period between when you do storms to make sure any transformations that may happen. But it's also really important that maybe you look at the mass. When you finish your study, you compare all your sampling with how much material is actually trapped in the device. We call this analysis and mass balance analysis. Another challenge we have with looking at percentage removal is irreducible concentration. I showed you this data before from the storm filter. Under 100 milligrams a litre, it actually the performance really starts to drop off and get lower and lower and a lower percentage, but it doesn't quite get to 0.0. That's because of a phenomenon called irreducible concentration. All treatment devices, this is another theory borrowed from wastewater or a technique borrowed from wastewater. Irreducible concentration, all devices will have a irreducible concentration. They will only be able to reduce it down to a certain limit. Under settling devices, will only be able to reduce it to what a particle can reduce in the time they have, settle in the time they have, or a filtering can only reduce it down to the size of the holes eventually inside the filter. So every technique will have a irreducible concentration. Also, how we can really consider irreducible concentration, though, it's almost clean water because you can't get any removal. It could also be the background concentration of what water is. So looking at, irreducible concentration for stormwater, some research has been done, and around about 20 milligrams per litre is about as clean as you can get stormwater for suspended solids. So now that was suspended solids. There was a lot to digest, and I just kind of wanted to really highlight the complexity and all these things you need to think about just with the easiest contaminant, which is suspended solids. When we start looking at other contaminants like nutrients and metals and other emerging contaminants like plastics and PFAS, there's a whole bunch of different other complications, and I won't dive into it, but the big concentration is still big. But speciation, what form is it in? Dissolved or particular, or the types of dissolved form it can be, that adds extra complications in removing it, or even its uptake into the environment. Metal complexing, what it's bonding with, that may mean it's harder to remove. Also, the other pollutants in the water, like if you're trying to remove heavy metals by cation exchange, different contaminants have more of an affinity to be absorbed. For instance, here, aluminium is likely to be more absorbed quicker than zinc. So if there's a lot of aluminium in the water, you may get a very low zinc removal and even a lower copper removal. So it is quite complicated, so you really need to have a protocol or a method to test it to address all these complex elements. So that's how I end up in performance testing. So let's get into that. Before I get into that, there's a couple of myths I want to talk about performance testing. And someone does a test and everyone goes, well, that's great. That's what we'll get from this device everywhere we apply it. And that just really overlooks the variable nature of stormwater. So these myths are like, if any sort of performance test results can be applied anywhere. As I said, performance is variable and influenced by many factors, and any study that you may get is only really relevant to the conditions that it was tested in. So the results can be used to predict effluent quality. That's another myth. I often see, this got 80% removal, so I'll apply it over here and I'll get that. That gets 80, that gets 50. I'll add up the percentage removals, and that's what the water quality we're going to get. That's really not possible because of the variable nature and so many other factors that are on that you can't really predict a water quality like that. And that you can actually assess the performance of any device from simply just taking one sample before and one sample after. I highlighted that before because it varies so much. You really need to have a look at how you collect the load for every storm over a period of time to understand if the treatment device or BMP is achieving your objective. So those are the myths of performance testing, but I'm not saying performance testing is not important. It's really important. It just needs to be done right, and it needs to provide the information that the user, like the people on this call who are evaluating a treatment, will need to assess whether it will work somewhere else as well as where it's worked before. So the role of a performance testing is to demonstrate the performance of a product or a product state. It's to give confidence in the performance of a BMP in certain conditions, and it's to benchmark this performance in relation to the testing variables and the environment and performance variables that we've just discussed. It allows comparisons between devices because they're tested the same way. So that's really important here. If we test everything the same way, we have more confidence in how one will be working against each other. And it also removes the need to test every installation because, you can't just go in and take one sample before and one sample after. So it's really difficult to go and test every stormwater install. So the role of testing is to demonstrate and give confidence to everyone and supply enough information to give that confidence to people. so that they can apply it in different places. Now, you can do performance testing in two ways. You can do it in the lab or you can do it in the field. Both have some merits, and I'll just run through them. Laboratory testing is really good as a preliminary evaluation of removal efficiency. You can use artificial sediments and silicons to put it in that's really repeatable and consistent, and you can be really fine and you can see how it can remove. It's really good to hold some things that are variable in a storm, like operating rates or particle size distribution or even concentration constant, just to see how something can work. So it's a really handy tool. It's also good for testing things that are difficult in the field, like scour testing. What happens when you get a 1 in 10 year storm? Well, that's, you have to be waiting for 10 years to capture that in the field, but you can simulate it in the lab, and it's really good for this resuspension testing, which drives whether a device should be placed online or offline. And when you're putting a device online, what's really important is the hydraulics. So it allows you actually then to develop empirical relationships for the head loss and the hydraulic effect, the driving head, the tailwater, the bypass flow capacities. And there's even methods, laboratory testing, for looking at the mass load capacity, or how long it will take before a filter clogs. Now, field testing is really expensive. 200,000 a go to do it properly. If you do it to the official standards that are that people want you to, and it's difficult. And it's not, as I said, it can't easily be replicated. You test a device twice and you'll get different results. But the big thing is it's real, and really things need to be real, and we need to really see them working for real in the real world. So it is critical that we field test. Why it's important too, because there's other factors that we can't replicate in the field, in the lab, such as the interaction of hydrocarbons and fine particles, the way a system may clog with sticky substances, the way metals complex, or that affinity of metals that I talked about before, or even fugitive solids. You really can't simulate that well in the lab and make it repeatable. So this is why we need to field test. So I talked all about the complexity, and I talked about the performance for testing, and the complexity is really addressed by the development of these verification and certification programs. These verification and certification programs have developed testing protocols that you can test to, and people will ensure that you've done the testing right and correct, and then other agencies will certify it also for approval. Verification is, so just to explain the difference between verification and certification, because this is really important. Verification is confirming something is true. So if I have a test or a performance study, I go get it verified by somebody. They'll go, yes, you perform, and I had a methodology for that study. They go, yes, you did that study like you said you would in the performance. That is correct, how you did that study. It doesn't mean to say that the study's right or wrong. It's just said that the procedure that was prescribed to do that test was done correctly. Well, certification is the approval. It infers certifying something to a regulatory standard or a requirement. So with certification, with the verification, you may have a verification agent that goes, yes, that testing was done correctly, but then the city council will go, okay, I'm going to certify that because I trust that data, and I'm going to say it's okay to use in my city. But the city then go, but well, I'm not really sure it really tested big enough storms for what we have here in Auckland. Maybe I say we have to size it more conservatively than what they're suggesting because we've got bigger storms and it can only treat less. Or we might say, as I said, you might say, we're only going to certify it for 80% instead of 90% because our sediment in Auckland is finer. So there's an opportunity there from city councils understanding the data and understanding their local conditions to put conditions with their certifications. So here's a bunch of the international ones. Above at the top list here is the verification programs and what they are. I'm not going to dwell on these. I'm going to push on. But down the bottom of the certification programs are, firstly, some are only laboratory, some are field and laboratory. Australia is a bit different. It has this body evidence pathway, and we have a whole paper and presentation in Stormwater 360 on the different certification and verification agencies in the world. But I'd really like to focus on the certification programs, and probably Washington take, which is a field study. And I really consider this the gold standard, and I'll explain to you why it is the gold standard, because it really picks up on a lot of these issues I've just raised. So firstly, it's a field study. It's using real stormwater with all the interesting things that can go on with it. It requires this flow proportional sampling, so the samples have to be paced and you have to do it in the field. It's got to be tested in Washington, because Washington actually has a finer particle size distribution, or Western Washington does, than the rest of the states, or tested in a place with a similar particle size distribution and also similar contaminant concentrations and speciation, and that's the form, whether it's dissolved or particulate. So it's addressing all those challenges and variables I said before straight away. And then it asks you to get approved or certified, you have to achieve certain benchmarks of removal. So to get approved for TSS removal, you need 80% removal. But they require demonstration of that removal rate at a certain concentration, and they provide concentration bands that you must sample into to prove that you're getting that removal in what is normal concentration. So for TSS, you have to it's actually between 100 and 200 milligrams per litre. You've got to demonstrate 80% removal. And also if it's really low concentration, you've just got to get average of 20 milligrams per litre. So that's taking into consideration the irreducible concentration. For metals, you have to get 60% removal of zinc between 20 micrograms per litre and 300 micrograms per litre. In industrial sites and stuff, or coming off a roof in New Zealand, we see like 3,000 to 10,000 micrograms per litre. So 60% at these lower removal rates is a good removal rate for just for the dissolved fraction of zinc. They require you to demonstrate those removal efficiencies at the treatable flow rate. And this is a graph here that shows percentage removal of copper. And this is different infiltration rates for the Filtera system, going up to 175 inches an hour. That was the removal rate, and that's 30% removal. And these are individual storm events. And they've plotted it, and they do a trend line, and it shows that at 175 inches, we'll probably be getting around 50% removal. So this qualifies, this passes. Also, the Washington tape protocol has now just introduced a maintenance protocol where after they give you an approval, they ask you to go out and test in the first year, test some of your devices in the field to show that it's operating at design rate. So the Washington protocol is really the gold standard in my mind. But still, you've got to bring that Washington standard to New Zealand and apply it, or approve it in Dunedin or in the far north or wherever you might be. So you need to be able to still look at that and see, is it really still right for my rainfall, my concentrations, my particle size? So I'm just going to move on. So how do we evaluate? And that's what I'm just saying. We need to consider the concentration. We need to consider the particle size or dissolved content of the data we're looking at. We need to consider the storm size and the flow rate, as well as looking at the efficiency, because they all affect it. We've got to evaluate, these criteria against what our local contaminants look like, and what our goals are, whether we want 80% or 60%. We should also compare what these results look like with other technology, especially our traditional technologies like a rain garden or a wetland and things like that. It's really important to understand the treatment mechanisms when you're evaluating. I don't like black boxes. If someone can't tell you how the pollutants are being removed, it could be just the randomness of their sampling. So it needs to be plausible, and you need to understand the treatment mechanisms that can be removing these pollutants. And then there's just, if it's really too good to be true, it probably is. And because stormwater pollutant removal, especially with dissolved and really low concentrations, is really, really hard. And you really need large systems to do it, like our traditional devices. So if it's really sounding too good, you need to look really deeply at the data and to see how that can be possibly happening. And there's a few tools here on how you can evaluate all this data. And obviously there's summary statistics, performance plots. I'd go to your local catchment management plans. I think we're on a round of rewriting them again soon. I'm not really sure. But that the catchment management plan should be work from the receiving environment up. We need to understand the stresses in our receiving environment to set controls upstream in the catchment to manage the stresses. So you can look at your receiving environment for what the pollutants are and what they are, the concentrations are. There's also stormwater databases. NIWA has a really good one, IRQUIS, which has stormwater data from all over New Zealand, and I encourage people to put more data into that because this really helps us what normal stormwater is. And then there is the International BMP database in the States, which has thousands and thousands of storms from different treatment devices and shows you what's normal and what's not. So here's some examples of summary statistics. It's important to look at median concentrations and not only mean, because data can be skewed by one large event. Performance plot, here's a performance plot on Filtera. So we instantly noticed something was different here. This is the inflow versus the outflow. Different colors of different studies, but one study we got, this is the Canterbury Uni, we nearly got 100% removal on all sorts of storms. So there's something different going there that we're looking at further to understand why Filtera could get nearly 100% removal at Canterbury Uni. And here's the BMP database. As I said, this is a table out of it for dissolved zinc removal. It's really quite good because it tells you the quartile range. It's got your 25 percentile concentration in is 24 micrograms per litre and a 75% out. So you can kind of estimate percentage removals here and the median value. I note they use median values because it's not quite a large enough data set. So just to reinforce that, so how would I apply this performance data to New Zealand? Well, you've got to understand your catchment, your contaminants of concerns, your typical concentrations and your typical particle size. And you've got to understand the testing, whether it was third party, whether it was verified or it was certified. You've got to consider that concentration on any observed performance metrics that you might be looking at. And particle size distribution, flow rate, sizing and speciation, all influences. Now, a really good example of that was what Morpham did for Auckland Council back in 2016, and Auckland Council should have this. This was the first Filtera application to Auckland Council. And they really looked at the data that we provided them from the Washington study, and they compared it to what was in Auckland. And it was a really good example of how to evaluate a device in a local context. But that's only been talking about performance. There's a whole bunch of other things, your maintenance frequency, how robust the products are, the warranties on them, your whole of life cost, your carbon and safety. These also are really important factors. And I don't know which one trumps each other. Is it more important to have something that's got a long maintenance frequency that doesn't remove as much? Or is it better to have safety's non-negotiable? We must have safety. But carbon, I don't know the importance of carbon because, if that means we have to go to a larger, more expensive device to address the carbon, it might affect the whole of life costs. So just to conclude, stormwater pollution is complex. There's more to pollutant removal than percentage removal. Performance is influenced by concentration, flow, particle size, and speciation. Verification and certification programs provide testing protocols to address complexity. However, these are not easily comparable. We all require good professional judgment and local stormwater knowledge in order to correctly choose the right solution for a local stormwater problems. So that is me. Thank you, Matthew. I hope everyone is still there.
lot to digest there. So there's if you have any questions, then do put them in the chat. Whilst we're typing in, I see a few coming in. I've just got a question to start us off, Mike.
Sure.
You spoke about percentage removal, and devices, do remove a percentage of contaminants that enter into them. The total percentage removal is variable, and that is a function of influent concentration. And also that load reduction is a very valid way of achieving a removal of or reducing the total load of a contaminant onto the environment. Is there a way that we can easily apply that to the context in New Zealand, where often the resource consent just says this percentage removal of that contaminant?
Unfortunately, not. You really need to be. There needs to be some discretion by the consenting officer or the regulator here, because really volume reduction has so many benefits, even beyond just the load reduction. It helps, cool cities. It helps to sustain environmental flows and streams. It reduces flooding. But that whole volume reduction part of green infrastructure, I guess, some municipalities or some councils only want green infrastructure, and I guess that's how they are kind of confronting that one, and not want. But there's always a need for an underground system sometime, because you can't always use green infrastructure. So not quite answering. There is no simple way of doing it, but that's the future, I guess.
And Scarlett has asked a really kind of probing question, which kind of picks up on that. She asks, why are we still using guidelines that are based on percent removal when these don't consider pollutant levels entering the receiving environment or reflect the true quality of water? So, as you said, low percentage removal looks bad. Are we looking to change the guidelines to better consider these factors for TSS and other contaminants?
Well, yes, I kind of was hoping with water reform and the opportunity to relook at catchment management plans that we could take a more of a modern view on how we determine what our stormwater regulations need to be. And as I said, it really starts with the receiving environment. What is the stress there, and what do we need to, reduce that load on the receiving environment upstream? Don't know where we are at the moment. Hopefully we'll get back round to it. And there's a lot of work going on at the moment. We're still going through the freshwater reform. Stormwater 360 is challenging a lot of the municipal city councils and the regional councils with simple statements like thou must get 75% removal. We need to do better that. We need to think about the load and our load we're discharging. So.
And fitting in with that, Richard Howard's asked an interesting question, is then, do you have confidence that the Kiwi consenting requirements for stormwater discharges are realistic and pragmatic enough to comply with? And I'm certainly thinking about where maybe ANZAC has been applied, or where it's purely an effluent concentration that's been written into the resource consent. Is that even achievable?
Yeah, I think that's a really big issue. I don't think it is achievable, and I don't think that people are really even looking at that monitoring data or not undertaking that monitoring in an appropriate way to really see if it's effective or not. If there's bad regulations, we just get bad application, and it's no good just setting a number because it makes everyone feel good. It has to be achievable, and from there we can get better. For instance, I've seen a lot of city council, a lot of regional councils set like a zinc effluent limit of 8 micrograms per litre. That's for total zinc, and that's just really unachievable. It's not possible. For instance, a trigger level in the US is 300 micrograms a litre. And that's where you start looking if you've got a problem with your discharge. And so that's really enforced in the US. And when it is triggered, there's action and people follow up. We've got a really low limit and it's probably breached all the time and no one does anything about it. So that's just really the two approaches that I hope we can fix, really.
And that brings, I guess, into question wider questions about consent monitoring and compliance and enforcement. But that's a whole nother webinar in and of itself.
Yes.
Francis has asked a really useful question, and you mentioned a couple of places, but do we know if there's going to be an updated contaminant load model in New Zealand? And obviously, I guess that will need to be region specific, because there's not a lot of data that's out there to kind of look at what's going on.
Yeah, I know Auckland Council and Morpham has been doing some work for them in Tauranga. There are different contaminant load models or catchment models being developed. I'm not sure if they're working back from the receiving environment, but more a goal or assumption that's just been set from a practical economic perspective. But yeah, I think many municipalities or city councils really need to, or regional councils need to put the hand in the pocket and get a model done for their location. So.
And we've got a lot of really good follow-on questions, because then Martin's asked an excellent kind of follow-on from that, is because PSD for sediment is so important to the efficacy of a treatment system, especially those, say, that are settling, like a hydrodynamic separator or a wetland even. At the moment, it's localized to the regional level, but shouldn't this then be localized even further within a region where there could be quite a disparate soil profile within regions? Even within certain catchments, you might have different PSDs and different requirements. Is there a point where it gets too detailed, or is there a point where we go, on a region-wide average basis, we are achieving what we need to achieve?
I guess that's the role of the catchment management plan again, right? To look at that. It could set higher standards in industrial areas in a catchment management plan, or in areas where there's finer particle size distribution, and lower standards in other areas to achieve a load reduction to the receiving environment. So it does give flexibility and you really and more efficiency if you do that planning process well, so yeah. But you don't want to make too many decisions at every resource consent stage, right? Because then no one can get an approval. We need to have a clear pathway with simple rules of application for different locations. Yeah.
And Julia, who sits in our engineering team, is a geologist. I was working with her and looking at PSD for certain places in the Waikato, and there might be very disparate PSDs, but of course the implication of that on urbanized stormwater runoff and the sediment that we're getting from the urban runoff, which we're predominantly treating, can be very different as well. So I guess there's an element of understanding, as even though the PSD for the soil might be different, once the catchment is stabilized, maybe there's some correlation.
Yeah, there's land use has an effect as well, definitely land use, but the surrounding soils have a huge effect on, because a lot of that sediment's blown and then it attaches with sediments or contaminants from, say, the kaita. It blows on, and so again, that whole build up and wash off and transportation model is quite complicated. And I know Canterbury Uni is doing quite some good work on that, looking at that too. And we need to understand that build up, wash off, transport model.
And then lastly, an interesting question from Matthew Taylor. With climate change and with increased high intensity storms, with higher rainfall, higher rainfall intensities becoming more regular, and of course then, as you said, that impacts the transportation of contaminants. So what used to be a 10-year storm and the types of contaminants that are transported with that is now changing. How does the climate change, how does that affect our evaluation? How do we ensure that we have, as regulators, that the regulators are putting the right sized devices in the right place?
Yeah, well, we're probably going to get more intense storms, which will probably mean higher concentrations, which means we'll get higher efficiencies. but we probably could still have we need to size our devices bigger, and otherwise we'll let more load out. So it just probably means that we need to really consider our sizing Storm and how we're sizing these things, because in general, I think we'll have higher efficiencies with climate change.
And I think that there was a paper at the Stormwater Conference that was
from Matt Murdoch and at WSP on that.
Yeah. So it is on the frame of mind, Matthew, there. So I think that draws us to a really neat conclusion. Just on 2:00. So with that, I'd like to say thank you all for your time and for some really excellent questions. It's not an easy topic, and it's a topic that will continue to be thought about and discussed at great depth until there is a New Zealand standard that has been adopted, because we have to take what we see from overseas and test the done overseas and apply that here. Thank you very much, Mike, for your comment and insight, as always. Learn something every time that you present a webinar that I get to be involved with, and look forward to seeing you all again soon. So we will be sending out a link to a recording of this, and there will also then be a link to sign up to the next webinar once that is announced in a couple of months' time. So with that, I'd like to bid you all thank you, and look forward to seeing you again soon.
Cheers. Thanks.